Okay, we ended up talking about, for our allosteric enzymes, meaning more than one subunit, there are two models to describe how they behave. And remember, the allosteric enzymes, usually you have that hard binding, then the easy binding, right? So how does it transition from hard binding to easy binding? And the concerted model, the basis of that is that what you have is all subunits changing at once. It's concerted change. And then there's another model we'll get to momentarily that's called the sequential model. And that means that we are changing one subunit and then changing the other ones. So in the concerted model, this is pretty neat, how we have an equilibrium between the easy binding, or the relaxed state, and the hard binding, or the taut state, or tight. And they're saying in this model that we have most of it in the taut state, the hard binding state, and that we have just a very little bit in the relaxed state, and then based on this equilibrium. So what happens is that the substrate will only bind to the relaxed state and take it out of the equilibrium, and therefore shift, due to Le Chatelier's principle, shift the equilibrium to make more relaxed. So let's talk about this equilibrium constant. This equilibrium constant is large, meaning that there's more product than there is reactant. There's more taut state than there is relaxed state. It does explain the sigmoidal effects. So let's take a look. Again, I have another very busy slide. So here, this is substrate concentration, and here is I guess, rate here. Yes, of course, it's rate. And so here, and we have Vmax up here. Let's just take a look at the left-hand side. The left-hand side is talking about the equilibrium constant. A larger equilibrium constant means that we will favor products. So this L of 10,000 is much larger than this L of 1. L of 1 means that we have equal amounts of our products and reactants, right? It's constant. An equilibrium constant is concentration of the products over the reactants. So if an L is 1, then we have equal amounts of the taut and relaxed state. So really, if you notice the shape of the pink, there is no hard binding because there's plenty of our enzymes that are easy binding, the relaxed state. But as you get bigger and bigger with this equilibrium constant, you're shifting it to more of the taut state so that you have hardly any relaxed state around. So we can describe the sigmoidal shape of our allosteric enzyme with this equilibrium constant. You have more sigmoidal shape is a larger equilibrium constant. And thus a higher concentration of our taut than relaxed. Over here on the right, we're talking about a C term or a cooperativity term. And this is where a lower value means that there is more cooperativity between the substrate and the relaxed state than the substrate and the taut state. A high C, which is this 0.1 here, relative to basically nothing, means that there's no difference in the substrate affinity for relaxed or taut. So it's not sigmoidal. So that the substrate, this higher C, means that the substrate likes both the taut and relaxed. But if you can see in the blue, the lower C means that the substrate likes the relaxed a lot more than the taut. So as you increase the C, or cooperativity term, you're losing that sigmoidal shape, meaning that there's really no difference between the taut and the relaxed. Okay, next we're going to talk about what does having an activator or an inhibitor do. This is, again, it's kind of busy, but I really, really, really like it. Okay, so I talked about my fish with Le Chatelier's principle, right? Did I talk about my fish? Okay, let's talk about my fish. My fish, we had several years ago. We had beta fish. And those of you that had general chemistry with me remember this story. Because what happens if you put two beta fish in the same fish tank? They eat each other alive, right? So you cannot have them in the same fish tank. But we did. But what we did is we put a plastic piece in between so the water could get across, but not the fish would just ram that plastic piece to try to get at each other. What a nasty pet, right? I don't know. Now we've evolved to 2 cats and 1 dog, but, you know, it's okay. All right, so imagine the left-hand side is the reactant side, and the right-hand side is the product side of my fish tank. And here in the fish tank, equilibrium is equal concentrations of water on both sides. Now, we know equilibrium is not equal concentrations. It's equal what? Equal rate going back and forth. But let's just say in this one reaction, the equal concentrations are equilibrium. What would happen if I scooped out the reactants?
Water
would go back to the reactants, right? What if we scooped out the products? It would go, water would flow this way until equilibrium was attained again. What if I added in more reactants? It would go that way. Okay? So all of the Le Chatelier's principle can be described by Dr. Barron's fish tank. We're not shopping anymore. We're using a fish tank. Okay, so this is the reactant side of my fish tank, and this is the product side of my fish tank. Okay? Fish tank right, fish tank left. And down here, it's scooping out. Okay? Down here, over here, and over here is scooping out. So the entire fish tank is just this part, the RO and the TO. Okay? Now, what happens is in the concerted model, what happens is either binding the substrate or binding an activator will scoop out reactant, our relaxed state. But it will scoop it out, but it's still available because it has another subunit to bind to. So we're scooping out. So what does it do to the fish tank? If I'm scooping out over here, what's it doing? I'm going to go from product. If I'm scooping out over here, I'm going to have more product come back, right? So here, our taut is going to get less. We're going to have more and more and more reactant until we have all reactant. And if I have more substrate binding and more activator binding, that is just going to be pulling the relaxed state out. So this blue is normal without an activator or inhibitor, okay? If I add in an activator, what is it doing? It's taking that hard binding out. It's moving this equilibrium so that the taut is making more relaxed until we have only relaxed, and then see the hard binding is gone. Now, if we add an inhibitor, it's going to scoop out on our product side. It's going to scoop out there and shift the equilibrium so that relaxed makes more taut, right? And then it's going to take it out. So then it's not available. So what's happening, compare the blue to the green, when you have more, when you add an inhibitor, it's going to make it more or all hard binding. Do you see that? It's all or a lot more hard binding. So an activator increases the amount of easy binding or relaxed state. An inhibitor increases the amount of taut or hard binding. An activator increases the amount of relaxed or easy binding by removing it from that equilibrium. And an inhibitor increases the amount of taut or hard binding by removing it from that equilibrium. Okay, what is happening to the K.5? The K.5, which is analogous to our Michaelis constant, means that a low K.5 means high affinity. So look at what's happening at the half of Vmax, or maximum rate. We are measuring our K.5. When you add an activator, what's happening to it? It's getting smaller, right? So you're increasing the affinity. When you add an inhibitor, the K.5 is getting bigger. So you're decreasing the affinity. Any questions on this one? A couple busy slides here.
Does taut mean a product?
No, taut is the conformation of the enzyme where it takes more than one collision in order for it's not easy binding. It takes more than one collision. So it's the form of relaxed and taut is how easy or what affinity does the enzyme have for the substrate? Will it take it in easy and form that enzyme substrate complex easy? Or does it take a lot of collisions to take it in? So the taut is an inactive form. It's not really going to make the product. Where the relaxed is the active form, where it's easily going to make the product. So there's two different things. There's an equilibrium between the two forms of the enzymes. I'm not talking about the reaction that it catalyzes. I'm talking about the equilibrium between the active and the inactive enzyme. Okay, the other model of allosteric control is the sequential model. And this has actually been called a more accurate model of behavior, and we'll talk about why in a second. So what they say is that we start all out in the taut form. It's all in the taut form, the enzyme, the hard binding. Then the substrate actually binds to the taut form, and that binding changes that subunit to the relaxed form. Once that one subunit changes to the relaxed form, it changes the conformation of the other subunits. Now this one is better because it matches our induced fit model of binding. Can you imagine? All right, so say this is the taut form active site, and I'm trying to put a square piece, or maybe it looks like this. I'm trying to put a circle substrate in, right? The substrate is a circle, but it's not really matching that, right? So what's happening is it takes a couple times for that circle to come in to my active site, and once it does, it changes to the circle, complementary. And that physical movement, that induced fit, that coming together from those electrostatic attractions between the active site and the substrate, or any kind of interactions, is an actual physical movement, like we saw with hemoglobin. And that movement causes movement in other parts and other subunits. and then it makes the other subunits have that circle form instead of the V form, right? So it's a little bit different. So it does do a better job modeling cooperativity. So this is the idea. Here, we actually do bind to taut, but it takes a couple collisions. See how, okay, we're putting a square, or I don't know what kind of shape that is, into a circle. So here, this is a different form. We have a semicircle active site, but we're trying to put something that's square into it. Let's just call that square, because I don't know what kind of shape that is. And so once it's in there, by induced fit, remember the Venus flytrap, that's the induced fit, not lock and key. But by the induced fit, it fits in there, it changes this side to relaxed. And once this side's relaxed, it changed that conformation, it's going to change the other one. So it's sequential, not an equilibrium between all taut and all relaxed, but that we are actually binding to the taut. Now, this does a better job of understanding our negative cooperativity, that's hard to say, where we're binding an inhibitor, and the inhibitor sort of locks that taut form. It locks it in place so that they're all the lower affinity. It doesn't allow your conformation to change from taut to relaxed. All right, so we're done with these two models. No math with the allosteric enzymes. So now we're going to go to the business part of the enzyme and really look at the active site. First, we're going to see how we determine what's going on in the active site, and then we're going to look at an example. Now, to understand what's going on in the active site, we need to know which amino acids are there at the active site and how they are in a spatial relationship to each other. So we identify the amino acids, the spatial relationships, and then we look at the mechanism. What steps are involved? And again, we are going to consider chymotrypsin. And chymotrypsin, again, catalyzes the breakdown or hydrolysis of peptides near phenylalanine or tyrosine residues. Now, a little bit about chymotrypsin again. We use p-nitrophenylacetate as a model because it's easily followed by spectrophotometry. I think one of them is colored and one of them is not. I'm not quite sure. But what they realized, so they used this as a model because we have an ester bond and we have something that's hydrophobic here. So it does a good job, and our enzyme chymotrypsin does work to cleave that. So what they did is they used it as a model, and they found that the mechanism by which chymotrypsin works to cleave this ester bond is a two-step process. First, the enzyme is going to form a covalent bond with the carbonyl of the ester. So it's going to cleave the ester here. It's going to release half the molecule. Then after it's released half that molecule, then we work to disentangle or cleave the bond between the enzyme and the carbonyl part. And so then we're left with the free enzyme and the other half. So again, in this model molecule, what we're doing is we're cleaving. We're breaking a bond. And the way that the enzyme does it is first to form a covalent bond with the carbonyl, then and release the other half of the molecule. And then what we do is we cleave that. Now, what they found by monitoring how much and when the kinetics of the release of the p-nitrophenolate, or one half of the molecule, and the other half. So what they did is they monitored for this guy and for this product. So both of those products. And they found that this first reaction was very quick. We had a burst. And then there was a sort of lag where we weren't getting acetate for a while until this burst was over. We had basically built up enough of this to push this reaction forward. Okay? So it's a two-step process. Now, so we figured out somewhat of the mechanism using that model. But we really want to find out which amino acids are going to be at the active site. And basically what we do is we find ways, so here's our enzyme and here's a serine residue. And by looking at the structure, scientists figured out this one might be at the active site. So what they're going to do is put a piece of masking tape over that one amino acid residue. So the masking tape is DIPF in this case. And it binds and sort of covers up our serine amino acid residue. Now, we've got to make sure that the enzyme's structure isn't changing. That by putting that masking tape over that amino acid residue isn't changing the conformation. So what they do is they do structural studies before labeling, and then they do structural studies after they label. And they find that the enzyme has not changed structure. The active site still looks like it does, but we put a piece of masking tape over that serine residue. And once they did that, they realized that the enzyme does not work anymore. They inactivated it. So by putting a piece of masking tape over this serine 195, you've rendered the enzyme inactive. So they know that that serine has something to do with the mechanism. They also found that a histidine in position 57 is also involved at the active site. They labeled the active site with TPCK, which you're going to have to remember the name and the structure. Just joking. I'm sorry. That's ridiculous. You don't need, I just want you to remember masking tape. Okay? That's all right. Okay. I'm not going to ask you what they use. That you cover the amino acid with something, a label. Okay? If you use tape in your answer, I'm fine with that. Okay? They cover the amino acid in question with something. And once they labeled it with this guy and made sure that the enzyme didn't change its structure, then they realized the enzyme was not going to be active. All right. One thing is that this group is much like our substrate with this phenyl group. So because the serine 195 and histidine 57 are required for activity, put a piece of tape over them, the enzyme doesn't work, then they have to actually be sterically close to each other. In space, they have to be close. And so what they did is some X-ray crystallography, and they showed that they were close to each other. I'm not going to go over this, but there is another aspartate that is also involved in the catalysis. And so chymotrypsin must be folded so that these two, or these three, are close together. And we have an active site. We sometimes say pocket. So here, the two that are really important are the histidine 57 and the serine 195. Do you guys need a break before I start the next slide? Because it's going to be like 20 minutes before